In 2016, NASA launched the groundbreaking OSIRIS-REx mission to collect a sample from the surface of the asteroid Bennu. After about 2 years of searching for the perfect landing site, the van-sized OSIRIS-REx made contact with the rugged terrain of the asteroid. However, due to the asteroid's fragile surface, the spacecraft had to work quickly. Simultaneously, it fired its thrusters to avoid getting stuck on the asteroid and prepared for an escape maneuver. In just under 3 seconds, the spacecraft's robotic arm created a 1.5-meter hole in Bennu and collected a sample of 250 grams of rocks and dust. After distancing itself from the asteroid and conducting multiple flyovers, OSIRIS-REx returned to Earth at a distance of about 101,000 kilometers from our planet. The spacecraft ejected the capsule containing the eagerly anticipated sample in the direction of Earth. During its journey, the capsule hurtled toward Earth at a speed of 43,000 kilometers per h and completed its 7-year, 4 billion-mile journey, landing in the Utah desert. In specialized clean room laboratories, scientists began analyzing remnants of the asteroid, searching for traces of life beyond our planet and clues that could unveil the secrets of life's origins here on Earth. When scientists first saw the capsule, they discovered some asteroid dust around the lid outside the main storage compartment. The most mysterious aspect was that the capsule was securely closed. How then did the dust end up there? When the OSIRIS-REx spacecraft landed on the asteroid, it produced a shock wave that blew some of the asteroid material into space. Some of this material ended up sticking to the probe when OSIRIS-REx quickly closed its lid after collecting samples. Small openings allowed bits of asteroid dust to escape. These initial fragments caught outside the main collection compartment are now being closely examined. Scientists have not yet opened the capsule, as most of the material remains sealed inside. So, how can a mere fragment of dust and space debris tell us about the early days of the solar system and unravel the mysteries of how life originated on our planet? The water present on Earth today is older than the planet itself, leading scientists to believe it was brought from space. In addition to water, asteroids can also contain crucial organic molecules. Scientists examined the extraterrestrial black dust collected from the corners of the capsule lid under the scanning electron microscope. They created 3D models of the particles and conducted chemical analyses. What they discovered from this small part of the sample was already remarkable: unexpectedly high amounts of carbon and minerals containing water. Discoveries like these are crucial for understanding the fundamental building blocks that shaped our celestial neighborhood and the processes that gave rise to planets. The potential role of asteroids in seeding ingredients for life on Earth billions of years ago is a well-supported idea in the scientific community. Not only water, but life itself may have been brought here by celestial bodies like comets and asteroids that collided with our planet in the distant past. Previously, astronomers had already detected fundamental building blocks of life on other celestial objects. For instance, the asteroid Hyugo contained uracil, a compound used in the production of genetic material in all living cells called RNA, and niacin, also known as vitamin B3, essential for energy production through metabolism. Even before that, scientists had detected organic molecules in meteorites found on Earth, but the question was whether they had been exposed to our planet's environment after the fall. Some astronomers believe that we currently lack the necessary technology to search for life in the Milky Way by studying distant exoplanets, but we can shift our focus to the examination of space dust. The idea is that asteroids constantly collide with distant worlds, generating powerful impacts that send debris into space. If some of these planets harbor life, the particles scattered into the universe may contain traces of the existence of life on those planets. Even small dust grains about 1 micrometer in size would be large enough to contain this information, but also light enough to be launched far into space. Due to the impact from collisions with just a 1 micrometer size, these particles are so tiny that a grain of sand next to them would seem like a giant boulder in comparison. Imagine reducing the width of a human hair to a fraction, and you'll begin to grasp the scale. This compact size would allow these particles to travel through the Milky Way at astonishing speeds, propelled by the inertia of the impact, encountering few or no obstacles in the vacuum of space. Some of these dust particles can reach the Earth's surface. An astronomer theorizes that about 100,000 of these dust grains land on our planet every year. Although it's not only asteroids and exoplanet debris that can carry life-bearing molecules. In the study, a scientist explored the interstellar clouds where stars are born. In a laboratory with conditions mimicking space, the scientist conducted experiments with common ices found in these clouds, ammonia, carbon dioxide, water, and even methanol, using a Van de Graaff generator. These ices were bombarded with high-energy protons, replicating the cosmic rays from space. As a result, the ice molecules broke apart and reassembled into more complex molecules such as amines, organic compounds containing nitrogen atoms, and amino acids. When our solar system took shape, these molecules traveled on carbonaceous or carbon-rich asteroids, eventually reaching Earth through cosmic collisions. A subsequent study revealed that if the asteroids were still warm after their formation, some of these molecules doubled in quantity in just 1 week. This suggests that the interstellar cloud from which our solar system emerged could have been filled with essential ingredients for life long before the formation of Earth, creating a safe habitat for its evolution. Currently, astronomers studying Bennu are trying to determine if it contains other precursors to earthly biology. However, more information is yet to be revealed. While uncovering the history of the solar system and the emergence of life here is exciting, there is another reason why scientists are studying Bennu. The asteroid is a potentially hazardous object, and astronomers are trying to figure out its future trajectory. So far, it is believed that the possibility of the asteroid colliding with our planet between 2175 and 2196 is about 1 in 2700. While this may seem highly unlikely, Bennu is one of the most threatening asteroids in our solar system that we know of, and certain factors at play could alter its trajectory. The asteroid is taller than the Empire State Building and about 7 times wider. Even the slightest change in its trajectory could put it on a collision course with Earth. Scientists are busy figuring out where Bennu is headed in the long term, using observations and mathematics to predict its orbit around the Sun. However, things have become complicated because Bennu is not only affected by the Sun, but also receives nudges from the Moon, planets, and other asteroids. Astronomers have marked 4 dates for upcoming close Earth flybies: September 2054, 2060, 2080, and 2135. In 2060, Bennu will be twice as far from us as the Moon, but determining its exact location is impossible, as it could be anywhere within a 30-kilometer space. And although it may seem insignificant on a cosmic scale, even uncertainties with such small numbers can dramatically affect calculations. Imagine Bennu as a car taking you to another city. If it deviates only 0.1 degrees from its route, it will lead to a significant deviation at the end of its journey, much like missing a turn on a road. The greater the distances involved, the further off course it will be. In 2135, Bennu will pass closer than the Moon, but predicting exactly where it will be becomes a real challenge. After the close encounter in 2135, this distance will increase further, and calculations will become increasingly confusing. Then there's the so-called Yarkovsky effect, another force acting on a rotating celestial object in space. It has nothing to do with gravity, but rather with heat from the Sun. When one side of an asteroid is bathed in sunlight, that side heats up. As the asteroid rotates, its heated side moves away from the Sun, exposed to cold space and radiating heat. All this heating and cooling produce a small thrust on the celestial body, causing it to change direction slightly over time. According to scientists' calculations, this force causes Bennu to change its trajectory by about 950 feet every year. This is how the asteroid traveled from the space region between Mars and Jupiter closer to Earth and the Sun. Although the odds of Bennu colliding with Earth are less than 0.4%, the probability is 5 times higher than being struck by lightning. It is also possible that researchers may be mistaken in their calculations, and the asteroid might end up hitting our planet. If Bennu were to collide with the Earth, it would leave a crater 6.4 kilometers wide, demolishing all nearby cities. But let's hope that astronomers know what they're doing. Meanwhile, the OSIRIS-APEX mission, formerly known as OSIRIS-REx, is far from over. The probe is currently headed towards an object near Earth, the asteroid Apophis, with a width of 365 meters. Apophis will pass very close to our planet in the near future, as close as the Moon. At its closest to Earth, it is about 355,000 kilometers away from us. The population will come even closer, within 1/10 of that distance, at just 35,500 kilometers in 2029. And then, in 2068, there is a small chance of a collision with our planet. The goal of the OSIRIS-APEX mission is to reach Apophis several months after its close approach, enter the asteroid's orbit, examine its composition, and assess its dimensions and shape. Asteroids of this size only approach Earth once every 7,500 years, but meteorites are not so rare. However, one meteorite has left scientists perplexed. This 0.45 kilograms rock found in the Sahara Desert several years ago may be the first terrestrial meteorite in history. Initial tests revealed that it is made of the same material as volcanic rock found on our planet. But that's not all. It also contains isotopes indicating exposure to cosmic rays and a fusion crust. This occurs when a rock passes through our atmosphere before impacting the ground. Essentially, scientists believe that this rock was thrown into space about 10,000 years ago when an asteroid hit Earth. It then spent thousands of years wandering through our cosmic neighborhood before finally being pulled back to Earth by gravity. If the hypothesis is true, this would be the first rock to leave Earth and return. In 2020, a fascinating astronomical discovery intrigued the scientific community. The meteorite known as El Ali, with an impressive weight of approximately 16.5 tons. However, the true mystery behind this colossal cosmic object lies not only in its grandeur, but in the secrets hidden within. During meticulous analyses of the meteorite, scientists stumbled upon an extraordinary finding: the presence of two minerals previously completely unknown to science, named elite and elkinsite. This revelation adds a layer of mystery to the understanding of the components that make up extraterrestrial objects, challenging conventional expectations about the mineral composition of celestial bodies. Although, so far, only a small fragment of the El Ali meteorite has been thoroughly examined, initial analyses already indicate the possible existence of a third unexplored mineral. The prospect of unveiling a new mineral element in the vastness of the cosmos raises questions about the mineralogical diversity beyond our atmosphere. The minerals elite and elkinsite, crystallized during the solidification process of the molten metal from the meteorite, provide a unique window into understanding the extreme events shaping these space rocks. Extreme conditions such as cosmic collisions and speeds exceeding 3,000 kilometers per h play a crucial role in the formation of these rare minerals, highlighting the complexity of extraterrestrial geological processes. The current challenge for the scientific community is to explore practical applications for these newly discovered minerals. The uniqueness of elite and elkinsite, coupled with the possible presence of a third mineral, opens opportunities for interdisciplinary research and potential technological advances. As scientists unravel the secrets of these cosmic minerals, the quest for terrestrial applications and a deepened understanding of their origin promise to expand our scientific and technological horizons. In our vast solar system, an intriguing phenomenon occurs in a specific region, the asteroid belt, situated between the orbits of Mars and Jupiter. This cosmic setting suggests the presence of a diversity of extraterrestrial minerals, yet unknown, eagerly awaiting discovery by the curious hands of scientists. The potential for surprising discoveries extends beyond what has already been identified, and the asteroid belt remains a celestial catalog to be explored. Meteorites, objects traveling through space that occasionally fall to Earth, are true cosmic time capsules. Their peculiar composition is not only limited to the presence of unknown minerals, but also extends to a myriad of peculiar atomic shapes and structures. For a long time, it was believed that crystals adhered to rigid and symmetrical rules, such as those found in diamonds or snowflakes. However, the revolution in understanding crystals occurred with the introduction of the theoretical concept of quasi-crystals. Unlike regular crystals, such as the mentioned diamonds, quasi-crystals defy conventional structures. They exhibit an ordered arrangement, but their patterns do not follow a regular repetition. This surprising discovery challenges previously accepted concepts and reveals an unexpected complexity in the nature of crystals. Human creativity, always driven by curiosity, led to the creation of quasi-crystals in the laboratory. However, uncertainty persisted about their natural occurrence. The intriguing question that arose was whether such crystals, with their unique and complex properties, could emerge organically in nature. Exploring these celestial and terrestrial phenomena opens the doors to a deeper understanding of the mineralogical richness of the universe. Nature, through its meteorites and peculiar crystals, continues to defy our predictions and inspire new questions, thus propelling scientific exploration beyond the limits of the known in search of answers that expand the horizons of human understanding. Subsequently, Luca Bing and his team made a remarkable discovery by finding a small piece of quasi-crystal in a meteorite that hit the Russian Far East. Surprisingly, the analysis revealed not just one, but three different types of quasi-crystals present in the same meteorite. This revelation included a type with a completely unprecedented chemical composition, adding an additional layer of complexity and mystery to these cosmic phenomena. The variety of quasi-crystals found in this specific meteorite highlights the mineralogical diversity existing in the universe and further questions traditional assumptions about crystal formation. This discovery not only opens new paths in understanding extraterrestrial geological processes, but also raises fascinating questions about the origin and evolution of materials in space. To contextualize the uniqueness of quasi-crystals, we can imagine the challenging task of tiling the floor of a house using pentagonal tiles instead of traditional squares or triangles. Quasi-crystals, in a way, are like these pentagonal tiles, presenting an atomic arrangement that doesn't fit perfectly, but at the same time, other atomic shapes fill the empty spaces uniquely and intriguingly. The complexity of these unconventional atomic patterns challenges established notions about order and symmetry in the nature of crystals. The discovery of these quasi-crystals in meteorites not only expands our understanding of mineral diversity on a cosmic scale, but also inspires researchers to explore practical applications of these unique materials, potentially influencing advancements in various fields, from materials science to cutting-edge technology. As we explore the origins of life on our planet, the fascinating hypothesis of asteroids being carriers of life gains prominence. The idea that these celestial bodies may have acted as seeders of life on Earth is intriguing, prompting us to consider whether this phenomenon also occurred on other planets. The possibility of asteroids spreading life seeds throughout the cosmos suggests that the fundamental elements for life existence may be more widespread than we imagined. Let's imagine then that asteroids play a similar role on other planets, carrying with them the essential ingredients for life and planting the seeds of existence at different points in the universe. This perspective leads us to speculate about the strange chemical compositions that could govern these distant worlds. Each planet, with its unique characteristics and specific environmental conditions, could give rise to singular and exotic forms of life adapted to its peculiarities. The chemical compositions of these planets can vary considerably. influenced by factors such as the abundance of elements in the interstellar region of the asteroid's origin and the atmospheric and geological conditions of the receiving planet. Unusual elements and complex molecular structures may give rise to forms of life that challenge our current understanding, expanding the horizons of biology and astrobiology. I invite all of you to share your ideas and theories in the comments. The exploration of the unknown is a collective journey, and the exchange of thoughts enriches our understanding of the universe. If you found this topic interesting, don't forget to support the channel by liking and subscribing to follow more incredible discoveries and new perspectives on our vast universe. Thank you for watching and being part of this discovery journey.